Welcome back to Homework Help for Math 2. Today we're going to be looking at Unit 4, More Functions, More Features, Lesson 2, Piecewiser. Start with the Ready section. Directions say solve each equation. All right, well, it doesn't get much more straightforward than that in terms of directions at least. Let's see how difficult this is going to be. So, number one, our equation is the absolute value of x equals 7. Well, whenever we're solving an absolute value equation, we basically need to account for two different scenarios. In this case, for number one, the thing inside the absolute value, which happens to just be x, that thing could either be positive or negative. We don't really know whether that thing is positive or negative because when you take the absolute value, you essentially just only take the positive, right? So in order to solve for x, we need to, again, account for the possibility that the thing inside the absolute value, which is x, it could be positive. It could be positive 7. The thing inside the absolute value could also be negative, because when you take the absolute value of it, you drop the negative. Well, this one's pretty straightforward because it's literally just x. So x is 7 or x is negative 7. So that is essentially our answer. If we want to write this a little bit simpler, we could simply say that x is plus or minus 7. And that is our answer for number one. Number two. Again, just like with number one, we have the absolute value of something, and that equals 3 in this case. And because we don't know whether that something that's inside the absolute value, because we don't know whether it was originally positive or negative, we have to account for both of those possibilities. So the first possibility is that the thing inside the absolute value, which is x minus 6, right? That could be positive. So it could be positive 3. Likewise, the thing inside the absolute value, which is x minus 6, that thing could be negative. Right? It's going to, x minus 6 in this case is either going to be positive 3 or negative 3, and then when you take that result, whatever it is, and you take the absolute value, you get positive 3. So now we just need to solve both of these equations, plus 6 and plus 6. So we end up getting x equals 9. And again, over here, we add 6 and we add 6. And so x equals negative 3 plus 6 is positive 3. And so for number 2, our final answer is x equals either 3 or 9. 2. Just like with number 1, we had 2 solutions. With number 2, we also have 2 solutions, 3 and 9. I'm not going to be checking all of these answers today, but just to be clear, if you were to take a 3 or a 9 and plug them back into the original equation, you will get a true statement. And that is a good strategy for when you're solving literally any type of equation, not just absolute value, but any equation. You can always take your answer, plug it in, and just double check and make sure that it is right. In the interest of time, I'm not going to be doing that today. The next assigned question is number 4. For number 4, we have negative 9 times the absolute value of m equals negative 63. Before I deal with the absolute value, I want to get the absolute value by itself. I want to isolate, and I want to have just the absolute value of something equals something else, right? So I got to deal with this negative 9 first, and in order to get rid of the negative 9, because it's being multiplied, I want to divide everything by negative 9. That's going to cause the negative 9 on the left to go away, leaving me with just absolute value of m. And that's going to equal on the right, I have negative 63 divided by negative 9. Well, a negative divided by a negative is a positive, and 63 divided by 9 is 7. So now I have the absolute value of m equals 7. Swap out an m for an x, and this is now identical to question number 1. So it's basically the same thing. Either the thing inside the absolute value is positive, or the thing inside the absolute value is negative. There's nothing left to do. I've just identified what m is, and so therefore m is plus or minus 7. Moving on to question 7. 7, I have negative absolute value of m plus 3 equals negative 13. Just like with 4, I don't want to deal with the absolute value until it's completely by itself on one side of the equal sign. And it's almost by itself, but there's a negative in front. And just to be clear, that negative, it's really a negative 1. So there's an invisible 1 in front of the absolute value, and so the negative, it's not just the symbol of negative, it's a number, it's negative 1. So to get rid of that negative 1, I want to divide by negative 1. On the left, that leaves me with absolute value of m plus 3. And on the right, I have negative 13 divided by negative 1, that's positive 13. Now I have the absolute value isolated, and so I can say, all right, well, if the absolute value of m plus 3 is 13, then it's possible that m plus 3 is just simply 13, right? Because the absolute value of 13 is 13. It's also possible that in this case, m plus 3 is negative 13. Because again, when I take the absolute value of that negative 13, I will get 13. I have to solve both of these equations, so I'm going to subtract 3 and subtract 3, so I end up getting m equals 10. Again, subtract 3, so 3. And I get m equals negative 13 minus 3. The number becomes more negative, right? The magnitude of the number will increase to negative 16. And so my final answer here for number 7 is that m equals negative 16 or 10. Those are my two solutions to this equation for number 7. Number 8. For number 8, my absolute value is already isolated, so I can now jump to accounting for the two possible scenarios here. So again, the thing inside the absolute value, which is negative 4m, that could be positive 64. It's also possible that the thing inside the absolute value, negative 4m, it could also be negative 64. Because in both cases, when I take the absolute value, the result is positive 64. Over here on the left, I want to divide by negative 4. That gives me m by itself on the left. And on the right, I have 64 divided by negative 4. A positive divided by a negative is a negative, and 64 divided by 4 is 16. On the right, I again want to divide by negative 4. Again, the negative 4 on the left goes away, so I get m equals. I have a negative divided by a negative, which in this case is a positive, and again, 64 divided by 4 is 16. So these are my two possible answers, and if I want to just summarize it succinctly, I can say that m equals plus or minus 16. Those are my two solutions. Next assigned question was number 11. This one's got a little bit more, I guess, stuff in it, but my overall approach isn't going to change. My first step here is to isolate the absolute value. So I have negative 2 times the absolute value of 2p minus 3, and then minus 1 equals negative 11. So I have to get rid of that negative 2, and I have to get rid of that negative 1. And just like when you're solving an equation, you know, if we had something like, let's say we had, I'll do this in red. Let's say we had something like negative 2x minus 1 equals negative 11. I think most people know that the first thing that you would do in this case is you would add 1, and you'd get negative 2x equals negative 10, and then you divide by negative 2, and you get x equals 5. Right? Just some solving a two-step equation. What we're going to do with 11 is essentially going to be the same process. So our first thing is we're going to add 1 to both sides. So that leaves me with negative 2 times the absolute value of 2p minus 3 equals negative 11 plus 1 is negative 10. And just like we would have done on the left in red, the next thing is going to be to divide by negative 2, because I have to get rid of that. So on the left, the negative 2's cancel, and I'm left with just the absolute value of 2p minus 3 equals, and on the right, we have negative 10 divided by negative 2, which is positive 5. Now that I've isolated the absolute value on one side of my equation, I can now account for the two possibilities here. Either 2p minus 3 gives us 5, or 2p minus 3 gives us negative 5. Because again, in both of those cases, the absolute value of that thing is positive 5. The first equation, I'm going to add 3 and add 3. So I get 2p equals 5 plus 3 is 8. Divide by 2. That gives me p is 8 divided by 2, which is 4. On the right, again, add 3 to both sides. The 2p drops down. Negative 5 plus 3 is negative 2. Divide by, no, not p. Divide by 2. And I end up getting p equals negative 2 divided by 2 is negative 1. So my two answers here for number 11 are that p equals negative 1 or 4, or and 4. I forget if it's or and, but my two solutions are negative 1 and 4. Moving on to the set section. Directions for the first couple problems here say, state the domain and range of the piecewise functions in each graph below. Use interval notation. And the next question that's assigned is 13. So we're looking for the domain and range. As a reminder, the domain of any function, not just a piecewise function, but of any function, the domain is the set of acceptable inputs, right? So what are all of the possible inputs that go into this function, that are possible to go into this function? And we're just dealing with x and y here, so as always, our inputs are represented by x. So what are all the possible x values here? So we have a continuous function here. So because of that, it means that we're going to be able to use interval notation, like the directions say, to say what's our lower bound, what's our upper bound, and then it's going to include all of the numbers between them as well. So for the domain, like I said, we're going to focus on the x's. The lowest x value that I see on this graph is negative 2. Looking at, I guess maybe we'll use a little bit of color on this one. So negative 2, which is that point right there. So for our domain, so just to be clear, the negative 2 is itself included in the domain, right? So the dot that got circled there, that's a closed dot, which means we include it. If that dot was open, we would not actually include the negative 2. It would still be the lower bound, but we would not be including the negative 2. Because that dot is filled in, it means we want to include it, and because we're including it, it means that with interval notation, we want to use a bracket, not a parentheses. I know that seems maybe like kind of a minor point, but if you used parentheses here, that actually is incorrect. So we want to use a bracket because we're going to include negative 2. So our lower bound is negative 2. And our upper bound, we're going to approach it the same way. Our upper bound is our largest value. It's smack dab between 6 and 8, which means it's 7. And again, we want to include the 7. So we want to use a square bracket. The range, we're going to do the exact same thing, except we're going to look at the y's. But other than that, it's this same concept. So for the range, the lowest y value that I see in this function is down here. And that's between -2 and -4, which is -3. It includes the -3, so we're going to use a bracket. Lower bound is -3. The upper bound it's also this point, and that largest y value is 6. So our upper bound is 6. We want to include the 6, and so we're going to use a bracket. So our domain is all of the numbers between -2 and 7, including each of them. And the range is all of the numbers between -3 and 6, again, including the bounds themselves. And just to be 100% clear here, we're including all, not just integers, right? So both the domain and the range include, for example, 1/2. They both include pi, right? They both include all of the numbers, not just the integers, but all of the numbers between each of the bounds. Next assigned problem was number 15, and we have a new set of directions here. Use the given piecewise function to answer the questions and sketch a graph. All right, so we're given a piecewise function that has 3 pieces to it. So each piece we have an equation, and we have a bounds on x that sort of tell us when to use which piece. 15a says find g of 1. So to find g of 1, if this was a, maybe a bit more, normal function, a non-piecewise function, we would simply take 1 and just plug it in. Now, in order to evaluate g of 1 with a piecewise function, before we plug it in, we need to know what are we going to plug it into, because we have 3 options here. There's the first one, the second one, and the third one, and they're going to give us different answers, but only one of them is going to be correct. So we got to figure out what are we talking about here. So our input is 1. So we have to figure out, well, where is 1 sort of, in here, right? Which bound, which group includes our input in this case, which is 1. And the one that we want is the middle one, because 1 is, so 0 is less than or equal to 1, which is less than or equal to 2. So we're talking about the middle one, which means in order to evaluate this, we want to use the middle piece. So now this is relatively straightforward. G of 1, we're just going to plug it in. -2 times 1 plus 6. -2 times 1 is -2. Negative. And -2 plus 6 is 4. So g of 1 is 4 for this function. 15b, find g of 4. Same idea. So we just got to figure out where is, in this case, our input is 4, so where does that fall in terms of our various groupings? And now for 4 is between 2 and 6. So that means that we want to use this piece of our piecewise function. So g of 4 is 1/2 times 4 minus 1. Half of 4 is 2, and 2 minus 1 is 1. Part C, find g of -5. Same idea. Where is, if our input is -5, what piece do we want to use this time? So -5 is between -6 and -2, which means we want to use this piece. G of -5 is, for this function, parentheses, -5 plus 4, close parentheses, squared. So -5 plus 4 is -1. Now, notice that I kept my parentheses, which actually ended up helping us a little bit. So we have parentheses -1 squared. -1 times -1 is +1. Now, if you were to try doing this on the calculator, if you try, and this actually applies for when you're squaring any negative number, if you type this as -1 squared and you press enter, chances are this is not actually the result that you wanted. It's not the result that you were intending to get or that you were expecting the calculator to give you. This is not parentheses -1 squared. Parentheses -1 squared gives us a different result. And the reason why the calculator gives us a -1 in the first case is because the calculator, when it sees the negative, it treats that as multiplication. And so with order of operations, exponents come before multiplication. So with the first example, the calculator does 1 squared, which is 1, and then makes it negative, which is -1. And notice that that's not what we want here. So again, I see this mistake very frequently. If you ever want to square a negative, make sure that that negative number is inside parentheses if you're going to use a calculator, because otherwise you're going to run into this problem, and this is a very, very common mistake that I see. But by keeping the parentheses, we actually were able to avoid that, and we got our final answer of 1. D. Find g of x equals 6. So this is it looks very similar to A, B, and C, but actually it's a little bit different, because with D, they're giving us the result. They're giving us the output here, what would essentially be our y value of 6, and it's saying what input results in a 6. And I'm going to make an executive decision here. We're actually going to pause on D and come back to it, because 15E says sketch a graph of this function, and I think once we see a graph of what's going on here, I think it will help make the solution for D make a little bit more sense. To be clear, we don't have to graph this in order to solve D, right? If D was the last part of this question, if E wasn't here, we could solve D right now. But I think that seeing a graph will sort of make the solution to D make more sense. So we're going to pause on D for a second. We're going to go to E, then we're going to go back to D. So E says sketch a graph of this function. And so we have all the information that we need in order to graph this. Looking at the right-hand section, we can see that our x values go from -6 to -2, then from 0 to 2, and then from 2 to 6. So on the x-axis, we need to be able to fit -6 and 6. And this graph is pretty much set up to do just that if we treat each box as 1. So I'm just going to treat each box as 1. So 1, 2, 3, and 1, 2, 3. That's, I think, sufficient for our scale for now. So the way that we can graph this is we're just going to essentially take each piece and graph that piece over the domain of that piece, so the possible x values. So the first piece, which again is parentheses x plus 4 squared, that's going to be our graph when x is going from -6 to -2. So -6 is 2, 3, 4, 5, 6. So -6 is right there, and -2 is right there. So between those two x values, we're going to want to graph parentheses x plus 4 squared. Now, there's a couple different ways to think about this. So this piece is a quadratic. This is a quadratic function, the first piece of this piecewise function. And the graph of a quadratic function is a parabola. And I'm not sure how comfortable people are with graphing the different components of this. So I think probably the easiest way that we can do this, again, without just sort of typing it into a graphing utility and sort of just copying an answer, if we take each of our bounds here, so if we take -6 and plug it in, that will give us a value that we can plot. And then if we take -2 and plug that in, that'll give us another value that we can plot. So let's just start with that and see what happens. So if we take a -6 and we plug it in, we get -6 plus 4, which is -2, and -2 squared is +4. What that means is when you plug in a -6, we get a +4. So I'll do this in, I'll just use the default. So you plug in a -6, and you get +4, which is right there. All right. Let's take a -2. When you take a -2 and plug that in, you get -2 plus 4 is 2, and 2 squared is also 4. So when you plug in a -2, you get 4, which is right there. Now, if you remember from the quadratics unit, the vertex of the parabola in this case is going to occur when x equals -4, which is also within our bound, right? -4 is between -6 and -2. So if we plug in a -4, we will get the vertex of our parabola. So -4 plus 4 is 0, and 0 squared is 0, which means, again, you plug in a 4, you get a 0. Well, we're right there. Right? This is probably sufficient to graph the parabola, but just to really drive home this point, if we plug in a -5, -5 plus 4 is -1, and -1 squared is -1 times -1, which is +1, which is right there. And if we plug in a -3, we're going to get -3 plus 4 is 1, and 1 squared is 1. So again, a -3 gives us a 1. And that just sort of provides, additional points for us to graph. And if we go ahead and connect these, hold on. Go ahead and connect these. We end up getting a parabola. The parabola starts and stops at -6 and -2. We don't want to continue because this piece of the piecewise function is only defined between -6 and -2. So you do not want to include the rest of this parabola because that's not part of this function. Taking a look at the next piece here. So the next piece is between 0 and 2. So between 0 and 2, so 0 and 2 is just to the right of the y-axis. And this piece looks like a linear function. So the first piece was quadratic. Now we have a linear function, -2x plus 6. Again, a couple of different ways that we can graph this. I think, in general, with a piecewise function, I think that there is value in sort of starting and stopping at the bounds. That just gives you a generally good idea of what it is that we're talking about here. So if we take our lower bound, which is 0, and plug it in, we get -2 times 0, which is 0, plus 6 is 6. So when we plug in a 0, we get a 6. So plug in a 0, we get a 6, so 3, 4, 5, 4, 5, 6. Okay, so we're right up there. This should not be surprising because if you take a look at our equation here for this piece, -2x plus 6, in a linear function, in this case, the 6 is our y-intercept, +6, and that's exactly what we got. You plug in a 0 into a function, and you're going to get, in this case, the y-intercept. So we got a 6, which really should make sense. Our upper bound was 2, and if we take that 2 and plug it in for x, yep, I'm not going to bother changing that. So we plug a 2 in here, we get -2 times 2, which is -4, and then -4 plus 6 is +2. So we plug in a 2, and we get a 2. The other way that we could have done this is just using the fact that this -2 in our equation is the slope of this line, -2. So what we could have done is from our y-intercept, we could have gone down 2 and over 1. Oh, do it again. right there. So we could have gone down 2 and over 1, and then down 2 and over 1, and we would have gotten the same line, essentially. So now we want to simply connect these points. And again, we only want the piece of this line that is from the lower bound to the upper bound. We don't want to go beyond 0 to the left. We don't want to go beyond 2 to the right, because that's only where this function's defined. All right. The last piece is from when x is between 2 and 6, which we should be able to fit. And we again have a linear function, but it's different. It's got a different slope, and it's got a different y-intercept. So, but other than that, it is still a linear function. Now, technically, this third piece does not include 2. If you take a look at our inequality here, right here, it says, specifically it says that 2 is less than x. It does not say that 2 is less than or equal to x, because we have 2 is represented there, right? X is less than or equal to 2. So when your input is 2, technically you're supposed to use the second piece. However, for the third piece, I actually still think that there's going to be value in sort of bending the rules a little bit. And even though 2 is not included, let's throw it in anyway, because it's going to help us graph this thing, right? So if we take a 2 and we plug it in to the third piece, we get 1/2 times 2, which is 1. And then 1 minus 1 is 0. So what that means is when we quote unquote plug in a 2, we get a 0. The way that we can indicate that on this graph is we can represent that with an open dot. So at 2, I'm going to put an open dot at 0. So again, for this function, when you plug in a 2, you get a 2. You don't get a 0. But for the purposes of our graphing, that's going to still form one of our endpoints for the line segment that we're going to draw in just a second here. The other bound, the upper bound, is 6, and it includes 6. So this is going to be a closed dot. Take a 6, plug it in. 1/2 times 6 is 3, and 3 minus 1 is 2. So when we plug in a 6, we get a 2. So 3, 4, 5, 6, and so 2. So that's right there. So again, we plug in a 6, which is, we plug in a 6, which is right there, and the result is a 2. Now we want to connect these, so we just draw a line, just like that. And that is our graph. Don't think we're missing anything. We can always label x and y if we want to, but hopefully by now we realize what's x and what's y. So that is our graph. Now, as promised, we're going to go back to D. So D, again, says find the input into this piecewise function that results in a 6. So as I said, I think that looking at the graph will help us understand how we can tackle a problem like D. The only time in this graph that anything results in a 6 is our middle piece, right? So the first piece and the third piece don't ever get up to 6. So in order to figure out, well, what value gives us 6, the only one that's even eligible is going to be this middle piece. And what we can see here is that we can see that we get a 6, just like when we did the lower bound for the middle piece, we got 0, 6. So looking at our graph, we know that in this case x has to equal 0. Right? That's the only real way to get a 6 in this piecewise function. Now, if we didn't have the graph, we would essentially still need to, figure out, well, for the parabola, how high does it get? It gets to a 4. It's never going to reach a 6, so we would have to know that we're going to discount that. We'd have to look at the third piece and realize that it's never going to get above a 2, so we have to discount that. And it's going to be a lot of the same work that we just did in order to create the graph. So yeah, that's how I would recommend that you solve something like D, is sort of think about, well, how high do each of these pieces get, or do they reach the value that we're looking for? And if they don't, then you know that you don't have to even look at that piece. And it turns out that here, the only way to get 6 with these bounds is with the middle piece. Next assigned question is number 17. So with 17, directions say, write the piecewise equations for the given graphs. So we have a piecewise function with 2 pieces, and we have to write the equations for them. So this function doesn't have a name, so we're just going to call it f of x. So clearly this is a piecewise function. And with a piecewise function, probably the best thing to do is actually to start with the inequalities. So the stuff on the right, sort of identifying what's my domain for each piece of the piecewise function. So looking at my graph, the first piece here, my x values go from 0 to 3. 0 to 3. So, and they include the 0 and they include the 3. So that means that my first inequality is going to be 0 is less than or equal to x, which is less than or equal to 3. And if your input happens to fall between 0 and 3, we're going to do something. And then my second piece is right here. And in this case, my x values go from 4 to 8, including 4 and including 8. So that means my second inequality is going to be 4 is less than or equal to x, which is less than or equal to 8. And if your input falls within that bound, you're going to do something else. So now we just need to come up with the equations that represent each of these pieces of our piecewise function. Clearly, both of them are lines, so these are linear functions. And that means it's probably going to make the most sense just to express these in slope-intercept form, y equals mx plus b. So all we really need here for each of these is we really just need to know, all right, what is y equals mx plus b for each of these lines? Now, for the first piece, we can get our slope, m, just by looking at it. So we can pick any 2 points. Doesn't really matter which 2 points we choose, because with a line, our rate of change itself does not change, so we can just pick any 2 points. Let's keep it simple. We can just start there and end there. The rise is -2, the run is 1, and so that tells us that our slope for the first piece is -2. B, as always, is our y-intercept. And what's nice about the first piece is that it literally intercepts the y-axis. Intercepts the y-axis right there. So that is our y-intercept, which is 1. And so b in this case is 1. All right, well, that wasn't too bad. So that means that our first piece of the piecewise function is going to be mx plus b, and m is -2. So it's going to be negative 2x plus 1. So for this piecewise function, if your input happens to fall between 0 and 3, you can evaluate that function by taking your input, multiplying it by -2, and adding 1. And that'll give you the result that you want. If your input is between 4 and 8, we have to do something different. But again, it's a line. So again, it makes sense to still use y equals mx plus b. But now we got to figure out the slope and y-intercept of the second piece. Again, getting the slope isn't too bad. We might as well just use that point and that point. So our rise is going to be 1, and our run is going to be from 4 to 8. That's a distance of 4. So in this case, our new m for the second piece is going to be 1 over 4. That's our slope. Now, to get the y-intercept, notice that this piece does not, the piece does not intercept the y-axis. So there's a couple different ways that we could get our value for b. One way, which is sometimes it's a little tricky, but in this situation it actually works out fairly nicely. One way to do this is to say, all right, I understand that this line currently does not intercept the y-axis, but sort of like what would it be if it did, right? So if we were to continue this line, this second piece, if we were to drag it to the left, maintaining the same slope and maintaining all the same properties, sort of, all right, well, where would this line intercept if it continued? Right? So if you apply our slope of 1/4, if you go down and to the left, down 1 unit and to the left 4 units, that actually puts us right at -2. So notice how even though the piece of the line that we really care about does not intercept the y-axis, sorry, audio went out. Notice that if we do continue this to figure out, well, what would the y-intercept be, it's going to be -2. So that's one way that we could get our y-intercept of -2. The other way that we could get it, if that, but sometimes that doesn't work out because sometimes the graph, it doesn't intercept at a clearly defined point, and so we have to guess. You don't want to guess. So if the graphing approach doesn't work, which it might not on another problem, another way that we can get our value is to essentially start by writing what we do know, which is the 1/4 x part, right? And we don't yet know what follows that, but we do know just by looking at our graph that if we plug in a 4, we want to get a -1, right? So you plug in a 4, you want to get a -1. So if we plug a 4 into this piece of the function that we have so far, we get 1/4 of 4, which is +1. But we don't want +1, we want -1. So that means we have to subtract 2 just to make the math work out, to make the graph work. We could have also chosen 8 here. And again, the graph says when you plug in an 8, we want to get a 0. And if you do 1/4 of 8, you get 2, which again means you have to subtract 2 to get the result that we want, which is 0. So a couple different ways that you can finish out that problem, either graphically or algebraically. Now we're into the Go section. Directions here say, beginning with the parent function f of x equals x squared, write the equation of the new function g of x that is a transformation of f of x as described, then graph it. All right, so with 19, we're told to take our parent function, which is f of x, and to shift it left 3 units, stretch it vertically by 2, reflect it vertically, and then shift it down 5 units. And we have to come up with an equation and then graph it. So again, we're doing all of this to the parent function, which is sort of like your basic quadratic, which is going to give us our basic parabola, so the main one. And then we can modify it a little bit to get our new one, which is g of x. So let's get the equation first. Whenever you take a function, in this case f of x, and when you shift it to the left 3 units, what that means is we're going to, everywhere we see our input, which in this case is x, we are going to replace that input. So I'll write this out. So we're going to go left 3 units. All right? What that means is you take your input, which is x, and that becomes x plus 3. All right? And specifically, right, you want to you want to kind of treat it as though it's inside parentheses, right? So in the parent function, notice that there's no parentheses on the right hand of the equal sign, right? It's just x squared. Now, we could write this as parentheses x squared, and we wouldn't change anything. With the parent function, those parentheses are unnecessary, and so we don't write them, even though they are technically there. In math, whenever we can kind of get away with not writing symbols, we tend to do that because it just simplifies things. But there is an invisible set of parentheses around that x. That's going to be important because when we start shifting this thing, and specifically when we go left 3 units and we're going to say x becomes x plus 3, now we're going to need the parentheses. All right? So we can sort of build our equation sort of as we're talking about it. So g of x is going to equal the x becomes x plus 3. And again, that is because we're shifting it to the left 3 units. And when you shift something to the left, it's going to be plus. When you shift it to the right, it's going to be minus. So x becomes x plus 3. Then we stretch vertically. I guess I should underline each piece here. So left 3 units, stretch vertically by 2, reflect vertically, shift down 5 units. So we've already shifted it left 3 units. Oh, and we need the squared. I almost forgot about that. That squared is definitely still there. Otherwise, we don't have a parabola, and it's way off. So it's parentheses x plus 3 squared. The next piece is stretch vertically by 2. So when we do that, so stretch vertically by 2, we take our new input, which is essentially this x plus 3, and so we're going to take that x plus 3, and we're going to slap a 2 in front. And we'll say, x squared and squared there as well. So when you stretch vertically, you multiply by 2, but the 2 does not get squared. So the 2 does not go inside the parentheses. The 2 goes in front of the parentheses. So please make sure that you're not including that inside it's not 2x plus 3, it's 2 parentheses x plus 3. Those are two different things. So that's going to stretch it vertically by 2. Reflect vertically, well, that just means that the 2 becomes negative. Right? When you reflect something vertically, it means that the coefficient on x becomes negative, or the coefficient on x squared becomes negative. And so here, instead of saying it 2, it's going to be negative 2. And then we shift it down 5 units. So when we shift something down, we shift it down 5. That means we're going to take like everything that we have so far, which is negative 2, x plus 3 squared. We're going to take the entire thing, and we're actually going to, keep it quote unquote the same, except we're going to, when all said and done, we're going to just subtract 5. Right? That's how you shift it down 5 units. Is you sort of take everything that you have, you don't really change it, but then at the end you say, oh, by the way, we're now going to also, in addition to everything else, we're also going to subtract 5, and that will shift the whole thing down 5. So our equation, we're going to minus 5 right there. So our equation is g of x equals negative 2 parentheses x plus 3 squared minus 5. And again, we shift left 3 units, that's the plus 3. We stretch vertically, that's the 2. We reflect vertically, that's the negative on the 2. And we shift down, that's the minus 5 at the end. Now, to graph this, if we wanted to, we could maybe get kind of fancy with our axes here and maybe focus on a particular quadrant, but I actually think that thinking through that's not really worth it. So if you ever don't really know what your graph is going to necessarily look like, and we could maybe talk about it a little bit more, but I just want to get this graph on paper. So I'm just going to center my axes, just right like in the middle of the graph. Oh, there you are. So I think it's just going to be easiest if we just like put them right in the middle. Is that in the middle? Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's an odd number here. That's strange. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Okay, whatever. That's fine. So this is our graph. And remember, we started with the parent function. The parent function for a quadratic, as you might recall, is going to look something like this: 0, 0, 1, 1, 2, 4, and then 3, 9. Let's see, is that going to fit? 1, 2, 3, 4, 5, 6, 7, 8. So 9 would be like up there. And then there's this symmetry, right? You connect those, that's going to be the parent function. But what we've done is we've taken the parent function and we have literally shifted it to the left, we've stretched it, we've reflected it, and then we shift it down. So what's going to happen is let's start with the vertex, which I still have on my graph here. Maybe we'll center it a little bit better. Right there. All right. So that is the vertex of the parent function, right? Just f of x equals x squared. If we shift it left 3 units, it's going to now be at -3. So it's going to be on -3 because we're shifting it to the left 3 units. Well, when you stretch a parabola, the vertex actually doesn't change. The vertex stays kind of where it is. It's not impacted by the stretching. So that actually doesn't do anything to our vertex. Reflect it vertically, well, we are currently on the x-axis. So when we reflect it vertically, it's still on the x-axis, so it still hasn't moved. And then we shift it down 5 units, so that's going to be, let's see, so that's -1, -2, -3, -4, -5. So our new vertex is going to be right there. That is our new vertex for this parabola. Now, if any of that was confusing, if you sort of didn't really understand sort of how we went from the old vertex to the new vertex, you can always just get a table of values and plot them, right? So if the whole transformation thing didn't make a lot of sense, you could just say, all right, well, what happens when you plug in a -3? And when you plug in a -3 here, you get -3 plus 3 is 0. 0 squared is 0. -2 times 0 is 0. And 0 minus 5 is -5. So that will also work, right? You could just start plugging in values, and that'll work for any function, not just quadratic and all this other stuff. So I think in order to finish out this problem, we could start moving other points from the parent function as well. But now that we've started getting this table, I think it probably is going to be easiest if we just sort of get a few more points and then call it a day. So if we go to the left, we're going to be at -4. And going back to my equation here, g of x, if I plug in a -4, I get -4 plus 3 is -1. -1 squared, so that's -1 times -1 is +1. -2 times 1 is -2, and -2 minus 5 is -7. So at -4, we're right there. So that's -4, -7. And I'll fill it in my table here. Now, because we know that -3, -5 is our vertex, we actually already know what happens at -2 because this parabola has symmetry to it. So because the -3 resulted in a -5, the -2 is also going to result in a -5, which means it's going to be right there. Oh, no, it's not. It's going to be right there. And let me get rid of my original vertex. It's getting a little confusing. Okay. But if you didn't see the symmetry, you could always just plug in the -2. -2 plus 3 is 1. 1 squared is 1. -2 times 1 is -2. And -2 minus 5 is... Wait. What did I do wrong? Oh, no, it's -7. not negative 5. I plotted that correctly. I filled in the table incorrectly. So negative 2 gives you a negative 7, not a negative 5. Yeah, so you can plug in the negative 2, you'll get a negative 7. That tells us that. We can't really plot any more points. If we try to plot more integer points, we're going to be off the graph. So we might as well just call it a day and plot this parabola just like that. Question 20 says to shift our parent function, f of x, and don't forget, this f of x is x squared. It's the parent quadratic function. So we're going to take our parent function, we're going to shift it to the right 1 unit, we're going to stretch it vertically by 3, and then we're going to shift it up 4 units. So I'm going to do this one a little bit quicker than 19. So when we shift a function to the right 1 unit, it means we replace our input. So whatever our input is, which in this case is x, we're going to replace that x with a x plus 1. Now we're squaring it, and even though there weren't parentheses in the original parent function, now we need them. We need parentheses around what is essentially our new input of x plus 1. So we're going to shift, we're shifting to the right. So because we're shifting to the right, it's minus. So we're shifting it to the right, so it's going to be x minus 1. We're going to stretch vertically by 3. So that means outside of our squared, outside of the parentheses, we're going to have a coefficient or a factor of 3. And then we're going to shift it up 4 units. So a vertical shift is kind of like maybe one of the most, it's one of the simpler transformations, because all it means is take what you have and then just sort of slap a 4 at the end, like plus 4. So a vertical shift sort of happens last, if you will, and because it's happening at the end, you just take whatever you already have and you just shift it up or down. In this case, it's up 4 units. All right, that's our equation. So g of x equals 3 parentheses x minus 1 squared plus 4. If you have access to graphing software, and if you type that equation in, you'll get the graph. But let's not do that for today. And again, if you wanted to get kind of fancy here with your axes and sort of put them anywhere other than the center, you're welcome to do that. I'm just going to put my x and y axes in the center of this graph and just sort of see what happens. So x and y. In our equation, when you're graphing a parabola, it is almost always a good idea to include the vertex, right? I guess maybe there's a handful of cases where you might not do that, but for the most part, when you're graphing a parabola, you're almost always going to want to include the vertex. And in this case, the vertex is going to occur when the thing inside the parentheses, the thing that's getting squared, you want that to equal 0. That's when the vertex pops up. So if you want the thing inside the parentheses, if you want that to equal 0, then x is going to equal 1. So I could make a quick table of values over here. So if I have x and y, and I know that my vertex is going to pop up when x equals 1, because again, that is what's going to cause the thing that's getting squared to equal 0. So you plug in a 1. 1 minus 1 is 0, which is what we want. 0 squared is 0. 3 times 0 is 0, and 0 plus 4 is 4. So it's the vertical shift. That's it. Come on. 4. All right. So let's go ahead and plot that. So 1 comma 4, we'll just use basic scale 1, 2, 3. 1, 2, and 3. There's a 1 right there. So 1 comma 4 is right there. That's going to be the vertex of this parabola. And we'll go to the left one and we'll go to the right one. So from here, if we go to the left, we've got x equals 0. So this is going to be on the y-axis. This is going to be our y-intercept. So if we plug in a 0, again going back to our equation here, plug in a 0, 0 minus 1 is negative 1. Negative 1 squared, which is negative 1 times negative 1, is positive 1. 3 times 1 is 3, and 3 plus 4 is 7. So we end up getting 7. Oof, doing that a lot today. So we end up getting 7. So 0 comma 7 is on our graph. So 4, 5, 6, 7, that's right there. And again, because a parabola has this symmetry that we've seen before, that means that at 2, we're also going to get 7. So we quote unquote know that that's part of our graph. And if you didn't know that, then just plug it in. 2 minus 1 is 1, 1 squared is 1, 3 times 1 is 1, and 3 plus 4 is 7. So you can get that 7, pretty easily if you want to, but because of the symmetry that's inherent to parabolas, we kind of already know that point's there. Any other points are going to be off our any other integer points are going to be off of our graph. So let's just go ahead and wrap this up. And that is the graph of this parabola after it has been transformed from the parent function.